All right, so now we're going to move to the world of climate change. So we wrote this paper. So I'm from Northeastern University. We wrote this paper with some collaborators at RISC and NASA Ames. And the whole idea with this paper is really getting high resolution climate change projections, right? So we have low resolution, and we have to get to high resolution somehow, and can we use machine learning to do that? So the World Economic Forum so of the top 7 global risks, 4 of them are directly related to some sort of climate change, right? So we got extreme weather events, water crises, failure to adapt and mitigation to climate change, and food security, right? So these all are crucial to basically everyone. So some of the important questions we may ask around these topics: how will climate change affect our food production? Will energy production be affected? Will extreme weather events increase in frequency, duration, and intensity? Does our infrastructure need to be adapted? Are financial markets and insurance companies going to be affected? So each of these are important to the economy, they're important to public health, and many, many areas. And we'll notice by actually looking at each of them, so if we're looking at food production, and we're interested in some area, some farm in the Midwest, we need to know what climate change is expected to do in that area, right? And we need uncertainty, we need a lot of information about that. And similar to if you're on the coast, and so forth. So in order to kind of understand what's happening with the climate, we have global climate models. And these climate models are highly dynamical, complex systems that model the entire globe for 100 to 200 years into the future. And we get data basically every day. There are many, many groups, more than 20 groups around the world working on these models. Each of them are ran with multiple initial conditions and greenhouse gas scenarios, right? So these greenhouse gas scenarios are, okay, so what if we cut down our greenhouse gas emissions? What if we actually have more emissions, and so forth? We can get these at yearly, daily scales, whatever we need. However, they are computationally infeasible to run at higher resolutions. So the spatial resolution we can get is between 50 kilometers and about 250 kilometers, which is about a half a degree to 2.5 degrees. And those have to be ran on massive supercomputers, right? So if we want to get them higher resolution, either we need to build faster computers, or we need to use some process to get them down to lower resolution, to high resolution. Though there is an approach, regional climate modeling, which you can only look at kind of one region and do a high resolution dynamical model there. But so we need to get high resolution climate change projections. And that problem in climate is called statistical downscaling. So statistical downscaling is kind of this process where we want to find this functional mapping between a low resolution climate data set and a high resolution. So throughout the rest of this talk, I'm going to be talking about precipitation, and this is kind of an example here. So on the right-hand side, we have 1/8 of a degree, right? So this is about 12 kilometers. And on the left side, this is about 1 degree, so about 100 kilometers, right? So we need to do an 8x resolution increase in this example. And we can pretty clearly see how it is really blocky on the 1 degree, right? So if we want to look at one given city, we don't have sufficient really information there. So we want to learn this functional mapping. And so there's been a lot of approaches that have looked at that have tried to solve this problem. One is, so the most popular is Bias Correction Spatial Disaggregation. And this is simply kind of a quantile mapping approach. It's very good at matching the distribution of our underlying variables. Automated-Statistical Downscaling is another approach that's used. This is just kind of linear regressions, SVMs, classification algorithms are in there too. Method of analogs is k-nearest neighbors approach, and kringing. which is Gaussian process. So some of the difficulties, they have weak performance. Basically, each of these do not perform as well as we need them to. And they don't actually capture, well, they don't explicitly capture spatial structure at the high and low resolutions, right? So this is kind of important. So if we look at the Automated-Statistical Downscaling approach, what we actually do here is we'll take one location, we'll learn a linear regression or something for that location, and then we'll learn a separate linear regression for every other location, right? So that right, so essentially with that process, we're not capturing any of the spatial information. And there are heavy computational requirements basically for each of these methods. So a similar problem. So a similar problem here is computer vision, right? Computer vision, spatial. There's this single image super resolution. And this is an example here, right, where they learn this mapping between the low resolution and high resolution images, which is very similar to the problem that we're trying to solve. And this is actually, so this is an 8x resolution increase right here. And I mean, obviously in this case, the underlying information, there's some prior distribution that knows it's kind of a face, right? And it can actually get some of that information from the low resolution. So we came up with a deep learning approach by kind of augmenting a super resolution CNN. And the super resolution CNN, essentially what you do, you feed in some image, right? You have some number of layers for convolutions, right? So you have X convolutional layers, and then you output the last convolution, basically. So what we do, so around the United States, right, there's all different topography and so forth. So we can't just take patches of some random location in the United States and run it through the network and expect it to do well, right? What we do is we include elevation there, right? So elevation is kind of capturing some topography in that information and handling some of the local biases. So we can concatenate those two. So now we have a couple channels. We can feed it through this network, right? So we have this, right, so our first layer, we have these 5x5 kernels, and we have 64 of them. We can kind of see the activations. Our second layer is just it's just a 1x1 filter. So that's basically just adding nonlinearity, and we have 32 of those. And then our output filters, we have a 5x5 output filter that actually returns our output. And so what we do here is we try to kind of minimize the loss between our output and our observations. So the way we do this in practice is if we have a single model, right, so running that for an 8x resolution increase is tough, right? Most of the super resolution models look at 2 to 4 resolution improvements. So what we do is we stack these networks on top of each other, and we do a 2x resolution increase at each level, right? So if we start at the left here, we have a 100 kilometer ESM, right? And then we have a 50 kilometer elevation data set. We can feed that through a network, and we can get a 50 kilometer downscaled result. And then we can feed that into another network with elevation at 25 kilometers, and then 12.5 kilometers, and so forth. And we can keep going down as far as we want, but then we're kind of introducing some noise into the data. So we kind of decided to stop at 12.5 kilometers in this case. So for our experimentation, so as I said, we're looking at daily precipitation, which is more challenging than looking at temperature per se, and that's the other kind of interesting problem. So we have precipitation at 1/8 of a degree, 12.5 kilometers. Our inputs, like we said before, precipitation and elevation. These elevations add multiple resolutions because we can get it at any resolution we want. For the training process, so we trained each of these networks independently, right? So we had 3 networks that we stacked. We trained them independently. So we do sub-image extraction to train the model. We just kind of extract 31 by 31 images out of it. And we train each of these networks. And then during inference, we can actually stack the networks together, do one feed-forward pass, and then we get our output. So how does this compare to other approaches? So some baseline approaches that we're going to compare to. So PCSD is the Bias Correction Spatial Disaggregation approach. This is a quantile mapping. LASSO is it's just a sparse regression. In artificial neural networks, that's just a regular ANN that's fully connected. In SVM, SRCNN, so this is one network doing the 8x resolution increase. And then our model DeepSD is doing the stacked approach. So what we do here is we randomly select 1,000 locations in the United States because it was infeasible to run some of these models over the entire United States. So we randomly select 1,000. And then we downscale from 2006 to 2015, right? So that's our test set. That's a held-out set. And we look at multiple metrics. So these metrics are computed by taking a single location, computing the metric, and then averaging over the entire United States, right? So for bias, we take one location, we'd say, okay, this is estimating 1 millimeter above on average, and then we average those across the entire United States to see what we get. So for bias, we have here, so we see our model DeepSD does surprisingly better than BCSD, and that's a bias correction approach. For correlation RMSE, so the predictability is much stronger than each of the other methods. Skill is basically a measure of how well we're matching the distributions. So are the PDFs matching? And it's between 0 and 1. So 1 would be basically a perfect distribution matching of the underlying climate variable. So as expected, PCSD does quite well. But coming in second is actually our model, right, at 0.947, which is not too far behind. And that, I was pretty impressed by that because I did not expect it to match the distribution quite so well. And then we looked at runtime. And this runtime was computed by downscaling 1 year of data. So how long does it take us to downscale 1 year of data for the entire continental United States? So SRCNN was the quickest here. And I should note that BCSD, after kind of talking to some people, it was slightly unclear on how to estimate the runtime there. It's kind of an interesting approach where we do this kind of quantile mapping thing at each location separately, and then an interpolation step and so forth. So that was a little bit more challenging to estimate. So when we look at this graphically, right? So when we look at this graphically, we can see DeepSD doing significantly better in the Midwest, right? So what this figure here is our RMSE per day, right, at each of these locations over the test set from 2006 to 2015. So if we look at maybe this location right here, we just compute that. We just compute the RMSE over our entire test set. And so red is high error, blue is low error. We see a lot more blue on DeepSD than BCSD. And we decided to compare these two because these are the two ones that we actually could downscale the entire United States. And they performed best in the previous evaluation. You notice a couple things, right, where we have in the Northwest here in Washington, where we do a little bit worse. And there are some really complex dynamics going on there. And these are just some other problems in general in climate that need to be worked on. So one of the questions is, can we capture extremes? This is very important. And so our process of doing this is we take the 90th percentile, right? So we take all observations that are greater than the 90th percentile. So the top 10% of precipitation days. And we can compute the same metrics as we did before. We can actually keep increasing this threshold and see how we're doing at higher extremes. So on the left side, RMSE, So we can pick DeepSD in blue and BCSD in green. And we can see as we increase that threshold, RMSE is actually getting, so RMSE for BCSD is increasing quite a bit, where DeepSD is actually doing pretty well at the extremes. And for bias, this is probably one of the more important ones, where we see at the extremes, our bias is not positive. It's not positive, which is a good thing, because these are normally very challenging to estimate. In correlation, we get kind of the same kind of results, where we have higher correlation than BCSD at all thresholds. Scale, kind of the same thing. So some kind of the novelty here, conclusion. So we're able to, with this new approach, we're able to retain spatial structure at the low and high resolutions. The multi-scale resolution enhancement actually improves performance significantly. And adding the auxiliary variable is able to encode the local biases. On the climate science side, we have a more generalizable spatial-temporal statistical downscaling model, where we did not have one of those before. It's also scalable, so we can run these on all the global climate models that we have, which is terabytes and terabytes of data. And we were able to improve performance on both daily and extreme precipitation. So that was a little bit quick, but our contributions here from myself, Evan Kodra at Risk, Arup Gangle at Northeastern, he's my advisor, Sangram Gangle at NASA Ames, Ramakrishna Namani, and Andrew Mikolas from NASA Ames also. Thank you.